Let's give it a start. Okay, we're already running late. Thank you for being here. So keep track of your time, okay, during the presentation. Let's start to keep it in the 15 minutes as it is expected, plus the 5 minutes Q&A. So for our next presentation, we're going to have Paul Peixoto from the Institute of Systems and Robotics of University of Coimbra presenting procedural generation of synthetic forest environments to train machine learning algorithms.
Thank you, Mikhail. So basically, I would like to start by making an acknowledgement. Most of the work that I'm about to present and it's the focus. You need to focus.
Okay. Focus on the presentation. Turn on.
Okay. Has been done by this guy, Rui Nunes, who worked with us. So basically, our background is in perception. We were working on perception for autonomous vehicles, as probably most of you guys here. And then we accepted this challenge to try to transfer some of our knowledge into the forest domain. Of course, this morning we already discussed some of the pros and cons about this issue. But one of the things that surprised us a lot was that there were no data sets, particularly no annotated data sets at all. So, and we started to think, okay, how can we are going to do this without any kind of data to allow our algorithms to be trained? So, and then we came up with the idea to try to do something which was already being done in the autonomous vehicle community, which is try to use synthetic data to augment the data they have available for training their algorithms. So that's why we came up with this idea of generating a bunch of synthetic images and try to see if they are going to be useful or not. So basically, this is the problem. So the shortage in data in a context where most of the algorithms we are using today are very, very data hungry. So and of course, I'm not going into too much about this because this morning we already talked about it. So even the fact, just to acquire the raw data is difficult. Now, on top of that, we need to label everything. And our idea was to use particularly leader data to try to experiment with some algorithms to make some kind of semantic segmentation, not on images, but directly on top of the free data coming from the leader. And as you can imagine, it's much more difficult to label leader points on the point cloud than to label pixels on the image. And so that's why we came up with the notion that, okay, we need to try to address data labeling problem, just to give you a perspective. So on probably one of the most used data sets for semantic algorithms in the autonomous driving context, Semantic Kitty, they spent more than 1,700 hours on the labeling process in a context where labeling is relatively easier than in the forest domain because everything is structured. So in forest, we don't have those geometric features that we have in an urban scenario or something like that, you know. So the idea is coming from, instead of using real world images, why can't we generate synthetic data? And if we have some control on the generation process, then we are going to have the labeling automatically solved. And the idea was to particularly to focus here on the procedural generation of the forest, because of course it's fun to have all these synthetic worlds being created, but if we have to place everything by hand, so we're not going to spend time on labeling, we're going to spend time placing the things to generate the scenario. So the idea is, okay, we just provide a few parameters. We've set up a few parameters. For instance, the density of forest, what kind, if they follow or if they not follow some kind of structure already, because In some scenarios, the trees are very well aligned. In other scenarios, they grow up completely random. So we define a set of parameters, and the idea is to come up with different sensor modalities. In our case, of course, RGB. With RGB, some kind of ground truth with the associated semantic segmentation, a depth map, and a point cloud. Okay, and that's basically what we try to do. And of course, we wanted to be able to generate a more realistic scenario, meaning that if we have a robot hanging on in this kind of scenario, we needed the entire generated simulation be large enough for the robot to move around. So, of course, this is not possible because we have a set of limited resources in terms of graphic elements, in terms of that correspond to some memory. So we needed to, think about a kind of a chunk generated scenario, meaning that we are going to just generate a chunk of data that is large enough to accommodate the sensing range of the devices we are trying to simulate. And then as we move by, we are going to generate the other chunks. And the huge thing about this is we rely only on a seed, a random generated seed. So basically, by providing the same seed, we are going to get exactly the same scenario. And this is quite cool. And of course, first thing we needed to generate was a terrain, and that this is something which is in the computer graphic community is very well established for a long time now. And once more, the gaming industry has already put a lot of effort here, so it's relatively easy to do it. We generate a terrain mesh using fractal noise. In our case, using a combination of multi-layers of Berlin noise, and by setting up a few parameters, we can have different scenarios in terms of terrain. Then we thought, okay, in order for this kind of things to be realistic, from time to time we have in forest we have paths, we have trails, so we need to simulate them. So we needed to come up with some algorithms to automatically place those trails on the scenario, on the terrain we have. So basically, we had to come up with algorithms that try to minimize the efforts to navigate on the terrain, and that's to avoid steep patches of the terrain. So try to follow. So everything was done automatically. So we don't need to say I needed to go from here to there to there. No, the trail is placed automatically. Then we need to add other different classes that typically we can find in the forest domains. So in our case, we assumed in terms of semantic segmentation, all these classes. Of course, people can group different classes together to have a less granular semantic segmentation. But we can have other things like this. We can have, for instance, we can have electric power lines. We can simulate them. We can add rail tracks to the scenario in order to produce more realistic scenarios for some of our applications. And that's basically it. So in terms of the object placement, we start by placing, of course, we have the terrain. We can put the trails on top of the terrain. Then we start by placing rocks, trees, and shrubbery, and then herbaceous plants. And I think I'm having so. And on top of that, and using the tools we have available. By the way, I forgot to mention that in this first generation of the simulator, we are using Unity, and that allows us to have different kind of light models. So we can simulate a normal midday scenario, or we can have early morning lights or late afternoon lights near sunset. Sorry, and that's for you to see. So this is a kind of a simulation of the things we are putting together, all the layers. So we start by the terrain, add the trail, then rocks, then the trees, and then beneath the trees, we put all the herbaceous plants or shrubbery, okay? So then the next step was to try to implement some virtual sensors, and of course, we wanted them to be as much accurate as possible to the real sensors. So of course, RGB cameras is easy because the most Unity already have them implemented. Okay, so we just need to define which kind of parameters we need to have on the cameras. Of course, Unity already gives us a pixel perfect semantic segmentation because we know exactly each point that is being projected on each pixel, what class they belong to, okay? Because we know which shaders we are using to render this pixel, and by knowing the shaders, we know exactly from which object they are coming from, so it's relatively easy. But for the depth camera, we tried to follow a similar approach, and the idea was to benefit from the fact that the depth maps are already being used in Unity on the GPU buffer, but the values they have there is the range only from 0 to 1, and of course we need some kind of metric information. Okay, so we need to calibrate this virtual sensor inside the Unity. So we need to come up with a setup where we have different planes on the world we are generating, and then we taking into account the parameters we were considering for the camera, try to calibrate, meaning to come up with a calibration curve that's given the range we would be able to get the depth in our case in meters. Okay. And by doing this, we are able to come up with this kind of depth map, so which ones more are really perfect in the sense that each pixel there corresponds exactly to the real depth that in the scene. Of course, we implemented a few error models, because if things are too perfect, then it will not be good for us for the algorithm. So we implemented several error models. We typically try to understand, and there are some people, fortunately, that already studied the generation procedure in a camera, and they explain models that could allow us to add some artificial noise to our images in order to be more realistic, in the sense they try to emulate better the reality. Okay, and then we did the same for the leader, and in the leader we try to be a little bit more precise, because of course in the autonomous driving community, people have already been doing this, but they typically approximates everything, because since the world they generate is much more structured, they don't need to be as precise as we need to be in the forest domain. For instance, in this case, they use colliders in order because we need to detect when the laser beam intersects each one of the objects. Okay, and what they do typically is they approximate, for instance, although we see in the computer game, we see this kind of very fancy tree, but beneath that we have a much more regular solid, in this case a sphere. Okay, this is being done only by texture, so there is no actual real surface beneath that. Okay, so it's the kind of the illusion they use in the computer in the computer game domain, in order for us to have real, very nice graphics, but with not complicated meshes to mess with, because they simplify the meshes, so they simplify everything, but they give us very nice looking results. So in our case, we need to be more precise. So we didn't use the normal colliders as people do. So we need to take into account things, for instance, like the transparency of leaves, because for sometimes the laser beam passes through the leaves, and then we can have a point that is beneath the leaf. Okay, so this is the bottleneck we have in terms of time in our simulator, because we spend lots of time here in order to try to come up with a very precise scenario of application. So then we simulated different patterns of sensors and so on. Okay, so this is what kind of data we have. Let me check. So this is different. And of course, everything matched perfectly in terms of the ground truth, okay? So in terms of system performance, so it's not real time. We would love to have it in real time, but it's difficult, mainly because of that feature in the laser. So basically, we are able to generate 1,000 frames in 3 hours. Okay, which is, if you compare it to the labeling process of other data sets, it is still a good improvement. So to finish, we try to do some very preliminary results with this. So basically, we train everything with synthetic data and try to check in the real data what we can get. Of course, don't misinterpret me. So I don't believe that by just using synthetic data we are going to solve our problem. No, not at all. So, but the idea was to try to feel if by adding this kind of images, we are getting something from that. Okay. So what we did, we trained with just using synthetic images, and these are 3 real world images. And as you can see, it's not perfect. It's far from being perfect, but it's something there. We got something. Okay. And another very interesting thing is that we were able to see whenever something fails, we were able to identify why it did fail. For instance, in this case, this barrier here was confused with trunks. And that's basically because on the training images, we never thought on using this kind of barriers on the synthetic images. So the synthetic scenarios, all the trails were plain. Okay, so we didn't have this kind of things. So, and this is one of the good things, because we can see, and I'm finishing, Miguel. We can see whenever we can see that there is in a certain scenario that things are failing, we can generate data, synthetic data, to try to compensate for that. For instance, this is a technique that is, for instance, Tesla is using right now. Whenever they detect that one of their cars was not able to for some reason to behave like it should be, what they do, they get the real data they have, the images or the video, even the video, they upload to one of their servers, and they have a huge simulator. I'm not sure if you saw it already. And what they do, they replicate on the simulator exactly the same situation that was on the car. And they, by looking in all different angles, they try to refine their algorithm. So I think this is one of the best things we can have from here, is the ability to address specific issues on specific scenarios. Okay. And to finish, we published out our synthetic data set. So for now, we have just around 3,000 and something images. But our idea is the next couple of months to extend this figure up to 15,000, and the idea is to go from there. Okay, and future work. I don't have time to go into it, so I would like to just leave, as Miguel said this morning. So we think that we need to try Unreal 5, and we did some experiments with it, and it has two major features. One is the global illumination model is amazing. So it's not that expensive in terms of computation. So we are excited because we think probably we'll be able to run the simulator in real time, which will be great because it will allow to close the loop, meaning that people could try the simulator in real time to make the vehicle move and get new images, for instance, for training algorithms to put everything running. I think that could be great. And well, that's basically it. Okay.
Okay, thank you. Okay, are there any questions?
Are you going to publish the method, not just the data?
The simulator. Oh, I forgot to mention. I think, yeah. Right now, we are redesigning the code to make it more modular, because the idea is being modular, people can contribute, for instance, for implementing a new sensor, implementing a new placing algorithm for very specific objects and so on. So this is it's part of our plans. Okay.
Cool.
So everything will appear on that page you saw. earlier. So we are going to update as we have more results. We're going to update that into that page.
That's awesome. Yeah.
First of all, it's great work. It's nice to see more people working on data sets. Vanessa will also present some work about that, but I think the fact that we have whole teams developing their own simulation will give it variety. And also all the dance annotation is great. And I had a question about the LiDAR annotation. Many LiDAR have different beam width. Do you take that into account? We have like this punctual LiDAR.
Maybe like that.
Actually, we have implemented different patterns of acquisition of the leaders. So is that what you mean? We have planar leaders.
I didn't think about that, but I'm thinking about the beam size.
Beam itself.
Yeah. It's configurable.
Okay, good.
It's one of the parameters you can define just before the simulation starts.
Excellent.
Okay. Okay. You're welcome.
Any more questions?
Actually, I have one question. First of all, great work. My question is, and this is common not only to synthetic images, but also real images. We've seen all the images are very bright, despite the different lighting conditions. But isn't it relevant to also simulate conditions such as, for instance, the existence of dust or debris? Because this is what we will find once you go into the forest and once you connect, you turn on the machine. So once they are working, there's going to be a lot of debris.
So we have been working with the CMU group that presented the paper this morning. And one of the things we noticed on the data, the real world data set they collected, was that there was a lot of motion blur. So one of the things we are planning to add quite a few things in that area, namely dust. We didn't think about dust, but I think it's a cool thing. But for instance, motion blur. We already have plans to incorporate it. So to generate a data or part of the data sets with motion blur, meaning that people can trade the algorithms. What happens if the data is not 100% precise? So, yeah, sure.
Thank you.
That will be very important in order for algorithms to be able to generalize to lots of different situations.